So I can create another one of these. So maybe I want to make a left child for the root. So I'm going to create a new binary node, new left child. There's a new binary node, and maybe this is a 2. And then I can say, hey root, set your left child to be new left child. So now I've got 2 different objects. There's this one out here, which is global, by the way, so I can talk about root and other methods. And I have this one internally here. Now this one's only going to live as long as I'm within these 2 braces. Kind of. So this name, new left child, is not going to exist anymore. However, since I've set it to be the left child of root within here, I could still get this in another method outside of here by saying root get left. It's still in memory, it's just that this name, new left child, no longer means anything outside of these 2 braces. So now I've created 2 different objects, this object and this object. And the way I created them was by following this blueprint over here, this class. So that's the way that object-oriented code works, is you create new objects. So right here, I'm also creating a new object. I'm creating a new Infix translator, this class here. Now, what does static mean? Well, static is entirely independent of a new object. So I don't need to create a new Infix translator to start my code. In fact, I can't, because the main method has to run from nothing. So when you have a static method, it's global. It means that there's only one of them for all my Infix translators. If I created a dozen Infix translators, there's still only one main method. So if I create something like, say, a static int counter, if I have one of these, no matter how many objects I have, they're all referring to exactly the same counter. So if I add one to, well, maybe it'll make more sense over here. Let's move it over to my binary node. So let's say that I have a static int counter over here. And every time that I create a new binary node, I'll add one to counter. So this starts at 0. I'll add one to counter. This one is calling this method, so I don't need to worry about that. And just to be sure, I'm also going to call this method up here, so I add one every time. So this counter will keep track of how many binary nodes I actually have so far, regardless. So if I want to get this value, let's create one more method over here. Public int get node count. So this will return this value of the counter. So after I create one of these root nodes, let's say that I go ahead and get the count. So if I do root.get node count, let's see what that gives me. And then after I've set the left child, let's see what that gives me. 1, 2. So since this is a global counter, even though I've created a new root, it doesn't get its own counter variable. There's only one for all the binary nodes. And then, so when I create a new left child, when it adds one to counter, it's not resetting counter to 0 because it's static. Static is, there's only one of them in the whole thing. So when I print out the node count here, so I could do root node count, or I could do new left child get node count. Same thing, 1, 2. So the idea of the static keyword is that there's only one of them in all of your objects. And the same is true of static methods. There's only one main method in all of my Infix translators, and it's only used once. The reason that we end up wanting to get out of this Infix translator then is that if I try and use this binary node root in this main method, it won't let me because I'm not allowed to use object variables, which is what this is, an instance variable inside of a static method. Because how would you do that? You haven't created a new Infix translator potentially. If I try and say root.getLeft, it's like, root? What? Cannot make a static reference to a non-static field root. So that's the reason that I've been creating the constructors immediately in the main method and just getting out of static methods. It makes it easier, and then I can talk about global variables like root out here. All right, tangent done. Let's see. If I want to create a tree, I can do something like this, where I just create the nodes, print out what they are, so on. What about actually doing something like printing out the entire tree? If I go look at this tree here, if I wanted to print out everything in the tree, how would I do that? Well, one thing I could do is I could just print out the left child, the root, and the right child, but that doesn't get me all the way down to the bottom of the tree. So we're going to use something called recursion to do this. So recursion is a technique that we use in computer science to basically walk down trees, typically, or through graphs, where we basically call a method over and over again on itself. Now, that might just scream infinite loop to you, and it should. So let's try creating something called public string print infix. So the infix is going to take a binary node. What should I call this? Current root, maybe? Sure, current root. And then what this is going to do is it's going to check to see if there's a left child or a right child from this particular node. So let's see, if current root dot get left is not equal to null. So you're allowed to do this, check to see if it's a null value. That won't throw an error, so you may have heard of a null pointer error. You only get a null pointer error if you try and do something with a null value. If you're just checking to see if it is null, that's totally valid. If current root dot get right is not equal to null. So if I have a left and right child, what I'm going to do is I'm going to print out the left child, the root, and the right child if I'm an infix. So I'm going to actually call print infix on my left child, because I have one. I just checked to see that it wasn't null. Plus my value, so current root's value, plus print infix. Here, let's put this on the next line so you can see it. On current root's right value. Otherwise, so what this is going to do is I'm actually going to call infix on my left child, and then I'm going to print my own value, and then I'm going to call print infix on my right child. So there's two other possibilities. Another possibility is, well, there's three possibilities, I guess. So what happens if my left child is null? If that's the case, I don't want to try printing my left, because that will die. So I'm going to call current root's value and print infix on my right, because it's not null. Now, what about the other situation? So if my left child is not null, then I want to print infix on my left child and not my right. And the final situation is, what if I have no children? What if I am a spinster node? Then I need to just print out whatever my value is. So the idea is that if I have a left and a right child, I actually call print infix on that child. So let me walk you through what it kind of looks like in a tree. So if I'm here, I call print infix on this guy. The first thing it does is it calls print infix on this left child. It basically pauses here and goes down here and says, hey, print infix on this guy. And it goes, hey, do I have a left child? It does. So it calls print infix on that one. So it gets down to here. So there's two print infixes paused at 2 and 7, waiting for return values from this guy. This guy goes, hey, do I have a left child? No. Do I have a right child? No. So it just is going to give back its value, which is a 2. This guy finally gets its left child. So if we go look at the code, it finally got back a 2 from this, and it gets back its own thing, which is a 7. Oh, but it needs to call print infix on its right child. All right, so pause there. So we have 2, 7, goes down this way, because it calls print infix on its right child, which calls it on its left child. It finally gets back this value. So this gets 5, 6. It calls print infix on its right, 11. Finally, this whole thing is done, and it gets it back to here. So we finally have 2, 7, 5, 6, 11, all which get back to here. This finally gets back up to the top, and its left child is done. But now it does the right child. Calls print infix on right, calls it on right, calls it on left, 4, 9, 5, all gets returned back up to 2. So because I am always returning if I have no children, this is the base case. So I will always return if I have no children. Otherwise, I'm actually going to be calling print infix until I get to the bottom of the tree. So it's going to be calling itself over and over again. So this is the idea behind recursion, is that you actually use print infix within itself to make this function work. However, there's this thing called a base case, which is this guy here, which will get you out of recursion so you don't have an infinite loop, because that would be bad and would cause your code to die. So let me comment this real quick. So that's the base case. This is, you have a left child. This is if you have a right child. And this one is left and right child. Recursive method that prints a tree in infix notation. Infix is infix order is left child root right child.